First, we'll focus on selecting the right hardware. We'll determine whether your sensors and DAQ hardware are up for the task at hand. This slide gives us an overview of a DAQ system. DAQ systems comprise of a sensor that connects to hardware, like a compact DAQ system, and the hardware connects to software through a bus, like USB. This software includes the driver software like DAQ. Signal conditioning is a general term that groups anything you have to do to the signal in order to prepare it for the next stage of processing. Now, this can take place within the sensor or in the DAQ hardware, or even some point in between. We'll go over them in more detail throughout the lesson. When we're taking a basic analog input measurement, we don't need much in the way of sensors, so we'll begin by focusing on the hardware and what we need to know to determine if we have the right hardware for our application. To do this, we'll need to ask a few questions, like, how many channels do I need? How fast do I need to acquire the signal? What's the smallest change of the signal I need to detect? If my hardware only detects 0.1 millivolt differences, but I actually need to detect something within the 0.05 millivolt range, then I'm out of luck. Another question we need to answer is, what is the expected minimum and maximum values that I'm going to measure, as well as how accurate a measurement do I need? What is the smallest change that I need to detect? To figure out what the smallest change our device can detect, we'll start by looking at the resolution, or number of bits of the device. You can think of the resolution as similar to the marks on a ruler. The more marks, the more precise the ruler is going to be. The higher the resolution is on a device, the smaller the detectable range it's going to have. The smallest detectable change in your signal determines the resolution that is required of your DAQ device. Resolution refers to the number of binary levels an ADC can use to represent a signal. To illustrate this point, imagine how a sine wave would be represented if it were passed through an ADC with different resolutions. This slide compares a 3-bit ADC and a 16-bit ADC. A 3-bit ADC can represent 8, or 2 to the third, discrete voltage levels. A 16-bit ADC can represent 65,536, or 2 to the 16th, discrete voltage levels. The representation of the sine wave with a 3-bit resolution looks more like a step function than a sine wave, where the 16-bit ADC provides a clean-looking sine wave. Typical DAQ devices have voltage ranges of plus or minus 5 volts, or plus or minus 10 volts. The voltage levels that can be represented are distributed evenly across a selected range to take advantage of the full resolution. For example, a DAQ device with a plus or minus 10 volt range and 12 bits of resolution can detect a 5 millivolt change, where a device with 16 bits of resolution can detect a 0.3 millivolt change. Many application requirements are met with devices that have 12, 16, or 18 bits of resolution. However, if you are measuring sensors with small and large voltage ranges, you can likely benefit from the dynamic range available with 24-bit devices. The voltage range and resolution required for your application are primary factors in selecting the right devices. We sometimes call the minimum change a device can detect its code width. To figure out the code width requires some simple calculation. We first take the device input range, which is just the total range of the device. For example, if it's a plus or minus 5 volt input device, it would have an input range of 10 volts. We then take the input range and divide it by 2 to the power of the ADC resolution. So, for example, a 16-bit resolution device would have the input range divided by 2 to the 16th, or 65,536. You can see that the bigger the resolution, the higher number you'll be dividing the input range by, which means you'll be getting a smaller and smaller code width as your resolution increases. The smaller our code width is, the better we can represent our signal. Applying amplification to an analog input signal is very similar to amplifying your voice with a microphone. If you tried speaking in a stadium for 100,000 people without a microphone, very few of them would be able to hear you. However, if you amplify your voice with a microphone, you can maximize the number of people that can hear you. In the same way, a small signal will not be able to use the entire resolution of the ADC unless a gain is applied to amplify the signal. So let's take a look at how the amplification setting affects an analog input signal. Assume we have a sine wave with a range of -2 to 2 volts and an ADC range of -10 to 10 volts. As you can see on the slide, if we applied an amplification of 1, which is no change, to our signal, we would only be taking up part of the total range, and thus using only 20% of our resolution. However, if we apply an amplification of 5 to our signal, we now have a sine wave with a range of -10 to 10 volts. Now our signal fits exactly in our range and we'll be maximizing the use of our resolution. Now let's consider a sine wave with a range of -6 to 6 volts with the same ADC range of -10 to 10 volts. So we can no longer apply an amplification of 5 because our sine wave would have a range of -30 to 30 volts, which exceeds our ADC range. So the only amplification we can apply is a 1. It's also important to note that the amplification is only used to maximize the use of the ADC resolution. If we're reading a 2 volt signal, we'll still see a 2 volt signal on our graph in LabVIEW. It's not going to affect your measurement. The amplification gains available on the DAQ device determine the device input ranges available. So, if a device has an available amplification of 5, we can measure a plus or minus 2 volt signal. But if it only has an amplification range of 1, we can only measure the total range that the ADC has, which is plus or minus 10 volts. Likewise, if we have an amplification gain of 100, we can measure signals down to plus or minus 0.1 volts. Accuracy is defined as a measure of the capability of an instrument to faithfully indicate the value of a measured signal. An ideal instrument would show the true value with 100% certainty, but in reality, instruments report a value with an uncertainty specified by the manufacturer. A common spec for this is absolute accuracy. This provides the worst case error of a DAQ device at a specified range, and most manufacturers provide formulas for calculating this in the device manuals. So it's important to note that this accuracy depends not just on the instrument, but also on the type of signals being measured and how noisy that signal is. Of course, the more noisy a signal, the more its accuracy will be affected. There's a wide degree of DAQ devices with a lot of different price points and how they improve upon accuracy. A basic DAQ device might have an absolute accuracy of over 100 millivolts, while a more expensive, high-performance device will have an absolute accuracy around 1 millivolt. Once you understand your requirements, you'll be able to choose a device that best fits your application. In this exercise, we'll use all we've learned in order to pick out the best DAQ device for some proposed DAQ systems. We'll use the required accuracy, resolution, and input ranges to help us choose. In this exercise, you used the code width equation, the device input range, and the device resolution to determine the most appropriate DAQ device to use for your measurement system in 2 different project scenarios. So in this slide, we'll briefly cover the topics of delta sigma and SAR ADCs. This is mainly just to make you aware of the different types of ADCs, so if you want to know more, please take a look at the white papers listed in your participant guide. The delta sigma ADC basically oversamples its analog input signal to provide a high resolution representation of that signal with low noise. Its resolutions usually range from 16 to 24 bits, so it's pretty high. The successive approximation register, or SAR ADC, takes a snapshot of the analog signal and then converts that whole snapshot into its digital representation of the analog signal. Its resolutions are a bit lower, so usually 8 to 18 bits. Again, if you want to know more about these ADCs, feel free to take a look at the white papers listed in your participant guide. In this section, we'll consider signal conditioning for our system. Let's take a moment to talk about signal conditioning. Signal conditioning is anything that you do to a signal to prepare it for the next stage of processing. Again, we see the components of a DAQ system, and signal conditioning can occur in the sensor, in the path between the sensor and the DAQ hardware, or in the DAQ hardware. Signal conditioning isn't required in all cases, but it's an important thing to consider for your system. Many sensors or signals need some sort of signal conditioning in order to be properly measured. For example, the signal from the sensor could be noisy, or it could be too small or too large for the range of your DAQ device. For instance, thermocouples, strain gauges, and microphones all produce a voltage in the millivolt range, making it hard to detect changes in the signal. This is why filtering and amplification are common signal conditioning techniques used with these sensors. There are 4 common signal conditioning methods for voltage measurements, which we'll cover in the following slides. They include amplification, attenuation, filtering, and isolation. First, we'll talk about amplification. We already talked about amplification when it came to hardware resolution and how to take full advantage of the range of the ADC. But amplification also helps increase the signal-to-noise ratio. The signal-to-noise ratio is simply the signal divided by the amount of noise. So for example, a 10 millivolt signal with 1 millivolt of noise has a 10% error in measurement. So the signal-to-noise ratio is 10. But what if we amplify this signal? If we add an amplifier with a gain of 1000, we'll boost the signal to a 10 volt signal. So we'll still have 1 millivolt of noise, which now has less effect. So the signal-to-noise ratio is now 10,000. This does mean, however, that we'll need to amplify the signal before the noise affects it, so we'll need to move the amplification closer to the signal source. The next form of signal conditioning is filtering. It removes noise and unwanted frequencies. So you can see in the first chart, we're showing our noisy signal in the time domain, and we can actually see multiple frequencies pop up in the frequency domain. After the filter, we see a nice clean signal and only one frequency. One of the main use cases is blocking noise that comes through with power lines, so the 50 to 60 hertz range. There are many different types of filters, and we'll actually go into more detail with them later in the course. Isolated signal conditioning devices pass the signal from its source to the measurement device without a physical connection by using transformer, optical, or capacitive coupling techniques. In addition to breaking ground loops, isolation blocks high voltage surges, like lightning strikes, and rejects high common mode voltage, thus protecting both the operators and expensive measurement equipment. Depending on the signal you're measuring, you'll need to be aware of the different isolation categories. This image gives you a really rough idea of the level of voltage that you might be measuring and the type of isolation you'll need to look for. In this section, we'll finally cover connecting the signal to the DAQ hardware. Before we connect any signals, let's locate the device pinout. The easiest way to find this is by opening up Measurement and Automation Explorer, or more simply called MAX, and expanding Devices and Interfaces. Once you locate your device name, go ahead and right-click that and select Device Pinouts. You can also use our NI Device Pinout app, which provides a handy reference on your phone, as well as the device data sheets. Now that we've found the device pinouts, we can actually go into review. So if you find the AI X plus or minus channel for the analog inputs, this is usually followed by a number which corresponds to the channel number. So for instance, if your DAQ card has 16 analog input channels, your pinout diagram probably shows the positive and negative terminals for AI 0 through AI 15. The plus and minus symbols refer to the differential input pairs. AI ground stands for analog ground, and this terminal is electrically connected to the ground of the instrumentation amplifier on your DAQ device. The reference point is used for reference single-ended measurements, and the bias current return point for differential measurements. AI sense is used as a common reference point for certain single-ended input terminal configurations. Notice that this DAQ hardware is capable of differential and single-ended measurements because it has an AI ground and an AI sense channel. Grounding issues are a common problem with analog measurements. So before you connect your sensors, you should ask yourself these questions. How is my signal source grounded? Does it connect to ground For example, is it plugged in, or is it a floating source? Like, does it use batteries, or is it a thermocouple? Does my DAQ hardware let me connect as differential, single-DID, or pseudo-differential? Steps to properly ground your system is, first of all, determine how your signal is grounded, and then we can choose a grounding mode for our measurement system. For the rest of our talks about grounding, Vs will refer to the voltage level of our signal source, and Vm will refer to the voltage measured by our DAQ device. Input terminal configurations take into account how the measurement hardware is wired to receive signals. So first off, I know this is a lot of information on the slide, but really you only need the details when you're developing your system. So I don't expect you to walk away with it knowing all the information on the slide. Just realize that the general recommendation is to use differential, as they reduce noise pickup and avoid ground loops. And that the only combination that we do not ever recommend is a reference single-ended setup with a grounded signal source. But let's go through a couple different examples using a differential setup with a couple different signal sources. So let's say that the signal source was a floating source. I know I'm going to use differential, so I look at my chart up here. I can see that the signal source is floating, so I'm going to use the left hand side, and I'd basically connect the positive probe to the AI positive terminal, and then I'd actually connect the negative probe to a bias resistor first, and then finally to the AI negative terminal. In the same sense, let's say that the signal source is now grounded. Well, what do? We check the chart. We can see I'm going to use differential. We can see that with the grounded source, we can simply connect the positive into the positive AI terminal, and then the negative into the negative AI terminal. In a demo that's coming up, we'll discuss a great guide that we have that should be your reference for choosing your different terminal configurations when you're setting up your system. So, an important job aid that we have is the field and wiring guide. So I'm going to show you all really quickly how to get to that. If we just open our web browser, you can see here I'm at the ni.com homepage. The easiest way to find the field and wiring guide is to simply search for it. So I usually just search for field and wiring guide. And then you can see the white paper is the first one that pops up. So the field, wiring, and noise consideration for analog signals. This is an extremely useful white paper. So whenever you're trying to figure out how to wire up your system and some grounding considerations, as well as noise considerations, take a look at this white paper. It goes in depth onto how you should ground your sources and the best ways to hook up your system to mitigate noise and make sure nothing wonky happens. So I would recommend everyone go to this page right now and bookmark it for later use. In this exercise, we'll practice figuring out which grounding mode to use, as well as how to connect the signal source to our instrument. In this exercise, you looked at two scenarios, one with a grounded signal source and one with a floating signal source. In this last section, we'll briefly go over the components of a current measuring system and how they differ from what we've been doing, which is measuring voltage. Measuring current requires a little bit of a different setup than measuring voltage and requires some different hardware. So current measurement shunts, or current shunt resistors, are actually resistors placed in the circuit for the purpose of measuring the current that flows across the shunt. These are fairly common electrical components and exist for a variety of applications. When you're sizing a shunt, it will be based on the measurement current range, output range, and power flowing through the circuit. So current transformers, pictured on the left-hand side of the slide, are sensors used to linearly step down the current passing through the sensor to a lower level, which will then be compatible with our measurement instrumentation. Another current measuring sensor type is the Rogowski coils, which are sometimes referred to as rope CTs. They're another sensor option for measuring current. They're similar in that they wrap around the load wire, so same as the current transformers, the wire actually goes in the middle of the sensor. The rope CTs also do the same thing, but they're more flexible. They have a much larger opening than the standard CTs, and the principal measurement is fundamentally different. Instead of using this hardware, you can actually buy specific DAQ hardware for measuring current, and these usually include internal shunt resistors. So a common way to measure current is to measure the drop-up voltage across a known resistor, aka a shunt resistor. So you'll then calculate the amps using the formula V equals IR. Another key fact is that the placement of the shunt resistor in the circuit is really important. So if the external circuit shares a common ground with the computer containing the analog input device, then the shunt resistor should be placed as close to the ground leg of the circuit as possible. So if you can see in the good figure, the shunt resistor is closest to ground. If this isn't the case, the common mode voltage produced by the shunt resistor may be outside of the specifications for the analog input device, which could then lead to inaccurate readings or even damaging the board. So in this demonstration, I'm just going to go through one of the example VIs for measuring current. So I've got LabVIEW open. To get to the example finder, I go to Help, Find Examples, and then once that opens up, you can either search for your topic or go to Browse. So I know where it is, so I'll just go into Hardware Input and Output. We're using the DAQ API. This will still be an analog input, and here it is, current software timed input. So you can see here, this kind of looks like the test panel that we played around with earlier and the other VI that we saw in the other examples. So again, we just got max current, minimum current. We do have a location for shunt resistor and some options for that. It can be external or internal. So some compact DAQ devices or modules have internal shunt resistors, so that's when we would select that. The default option is that DAQ will kind of choose for you. So if you're using a module that has an internal shunt resistor, it will automatically choose that internal shunt resistor, and then if it doesn't, you'll have to use an external one. Then we can input the shunt value here. So to view the block diagram, let's go to Show Block Diagram, and you can see here that it's pretty similar to our voltage VIs. So we have our Create Virtual channel right here. This is an AI current channel. So this is where you select the analog input, I'm going to choose voltage or some other measurement type. Here we have current. And then we have our shunt resistor values, and our shunt values, as well as physical channel. And then we go into the DAQ start, read, close, and then we're done. So not too different from our previous experience with the DAQ API. This first question is, which of the following grounding modes is not compatible with the grounded signal source? The answer is B, referenced single-ended. List 4 signal conditioning techniques common with voltage measurements and how they help produce. Suppose you have the following pinout for the. Suppose you have the following. So, in this first lesson, we learned how to make a voltage or current measurement.